In this video, we are going to discuss about AVL tree named after Adelson, Wilsky, and Landis, the inventors. And this tree is also called as self-balancing binary search tree or height-balanced binary search tree. So it is a type of binary search tree. So we already have a binary search tree. We should know why we want to move on to another kind of tree like an AVL tree like this. So first we'll be discussing the working of binary search tree. A simple example, how does a binary search tree works and what is it? And why, what is the drawback of binary search tree? And then we move on to the AVL tree, the working of AVL tree and how it is actually balanced. So binary search tree is a kind of binary tree. So each node will have not more than two nodes. That is binary tree, right? Like when you have a tree structure with not more than two nodes, then that is called a binary tree. So this is a binary tree. Okay. A node will have a 0 child or 1 child or 2 children. So everything is allowed. So that is not more than 2. That is a binary tree. And a binary search tree is a value tree. So each node will be having certain values like 120 something and all. So here the values are arranged in such a pattern that like the root node's value is always greater than the left node. So I'll be having 90 here, 100 here, it is allowed. And the reverse is not allowed. So the values that present to the left of this root node, any node should have a lesser value than the root node. So here when I consider, and to the right of it, it should have a greater value, like 150. Okay. So when I take this root node, 90 is lesser, so it is present in the left side of it, and 150 is greater and it is present in the right side of it. So this is the general logic. Now consider this node. The value of this node should be lesser than 100. Since it is present in the left side of 100, it should be lesser than 100. And it should be greater than 90 since it is present in the right side of 90. Okay, so I can have it as 97. So 97 is less than 100 and it is greater than 90. So this is how it actually works. Even the subtree follows the same rule. All the nodes that present to the left side should have a lesser value and all the nodes that present in the right side should have a greater value. So that is the common thing regarding this binary search tree. Now coming to the drawback of binary search tree, the reason why we propose binary search tree is, as the name indicates, it is specifically used for searching technique. See, when I want to search for an element in a binary search tree like this, okay, in case if I have a tree structure like this, and I know all the values that present to the left side has a lesser value and all the values to the right has a greater value, right? When I am searching for a value, okay, might be I haven't mentioned any of the values over here since I just want to search for this node. So how can I do? First, I'll compare to the root node. If the value is lesser, I search only in the left subtree. So I ignore the right subtree as a whole. Okay, so only this will be considered at the time of searching. And again, the value that I'm searching for is greater than this node. So I'll be ignoring this half and I'll just focus on this half alone. So each time I'm going to divide the tree by 2. And that is the specific reason, like why we call it as binary search tree. It is easy for searching in a binary search tree. Okay, so we just want to divide it by 2 each time. So only a half a portion of the tree will be verified each time. So the complexity for searching will come under order of log n category. Okay, so that is exactly the reason why we are going for binary search tree. But still, there is a problem with this binary search tree. And consider this example for binary search tree. If I just want to insert some elements in ascending or a descending order like this, 10, 20, 30, 40, 50, 60, 70, and 80. If I want to do an insertion for all these elements like this, so I'll start inserting the first node. It will be the root node. And the second node, 20 is greater than 10. So it comes to the right side of it. And the next node to be inserted is 30. 30 is greater than 10. So comes to the right. And 30 is greater than 20. Insert it over here. And again, 40. 40 is greater than 10. 40 greater than 20. 40 greater than 30. So I have to insert it here. and 50, 50 greater than 10, 20, 30, 40. So I have to make an insertion to the right hand side. Now 60 is again greater than all the nodes. So it comes to the rightmost node. So we keep on inserting like this. Now the tree structure looks like a linear tree. If I want to search for 60, I will start from 10, keep on comparing all the elements of the node. So the complexity of this kind of tree goes like order of n, but the actual complexity we have decided is order of log n, but it comes to order of n complexity. Okay, since there is no restriction regarding the height of your binary tree, so it can grow in any of the order. So that is a problem that we face in binary search tree. So we'll be moving on to an height balanced tree. And that height balanced tree is called an AVL tree. So AVL tree is a type of binary search tree in the sense the values are going to follow the same structure and each node will have not more than 2 nodes. So everything is fixed along with the rules of your binary search tree. We are going to propose one more factor called a balance factor. So we'll be having something called a balance factor here. And the balance factor for each node is calculated as height of left subtree minus height of right subtree. So we'll be finding this balance factor. And for AVL tree, the balance factor should lies between either 1, 0 or -1. It lies between -1 and 1. Okay, so the value of binary balance factor for each and every node is calculated after every insertion and every deletion. And the balance factor should lie between 0 to -1, -1 to 0, 1. Okay, so it should be either 1, 0 or -1, not more or not less than this. Okay, so I'll just take one example and I'll show how to calculate the balance factor. I just ignored the values in the node. Consider a tree structure like this. Okay, so here this node, for each node we have to calculate the balance factor. So when you can take this leaf node will have no child at all. So the balance factor for the leaf node will be 0. Okay, and consider this node has 1 in the left subtree. The height of left subtree is 1 and the height of right subtree is also 1. We are just speaking about the height. So whenever you are speaking about the height, you have to take the longest branch and the number of edges in the longest branch will be taken into constraint. Okay, so for this node, height of left subtree is 1 and height of right subtree is 1. So 1 minus 1, the balance factor is 0. And consider this node and I'm sorry. Yeah. For this node, when you consider this node, the height of left subtree is take the longest branch. So both has the same count, either take this branch or take this branch. And the number of edges present in the longest branch of left subtree is 1, 2. So in left side, you have 2 and right side, you don't have any branch at all. So the balance factor for this node is 2. Since height of left subtree is 2 and height of right subtree is 0. 2 minus 0 is 2. And consider this node. For this node again, you have to take the balance factor, height of left subtree. The height of left subtree is, you have to take the longest branch. So 1, 2, 3. Number of edges in the longest branch is 3. So this is 1, 2, and 3 for the left side. And for the right side, you don't have any branch at all. So the balance factor for this node is 3. Okay, so for an AVL tree, a tree to be in an AVL structure, the balance factor should be either 1, 0 or -1. It should not be 2 or 3 or not allowed. Even -2, -3, nothing is allowed. Okay, so what happened if the balance actually matches? If this matches, what we are going to do? Okay, so we'll be rearranging the things. Okay, so now I'll show you how to make this unbalanced to a balanced tree. Like when there is an imbalance occurs, how we are going to make it into a balanced tree. And we have certain kind of rotations for it. So first of all, like when the tree just have a single node, okay, it doesn't have any left subtree or right subtree. So the balance factor will be 0. So for a single node, not an issue. And when the tree has two nodes, it might be either a left child or a right child, right? One or only two possibilities. So in this category, so what is the balance factor for the leaf node? It is 0. There is no child at all. And for this node, you have one, the height of left subtree is 1 and height of right subtree is 0. Okay, so the balance factor is 1 minus 0 is 1. And for this node, the height of left subtree is, there is no left subtree, and the height of right subtree is 1. So it is 0 minus 1. The balance factor is minus 1. So when there is only two nodes in the tree, the balance factor will either lies as 0, 1 or minus 1, not more than that. Okay, so we'll move on to the next category where when the tree has more than two nodes, that is 3 nodes. For example, if a tree has 3 nodes, there are 3 possibilities, or like there are few possibilities in which a tree can be arranged like this. Okay, so this is one possibility, this is another possibility. Another possibility is a criteria like this. I'm just drawing all possible criteria when a tree has a 3 node. Another possibility is having it like this. Yeah. Okay, so these are all the 5 possible ways in which a tree can be arranged when a tree has 3 nodes. Okay, so when a tree has 3 nodes, it might be either arranged in this category or everything to left or everything to left, right, or left to right or right to left. Okay, so these are all the possible arrangements that a tree can have when it has the 3 nodes. Now calculate the balancing factor for each and every category. For all the leaf nodes, the balance factor is 0. The reason is there is no left subtree or right subtree present. So it is all 0. And consider this case for the root node. You have one left child and one right child. The height of left side is 1 and the height of right side is also 1. The balance factor for this root node is 0. So this is in a perfect category. Okay, when the criteria looks like this, we don't go for any rotations. This is perfectly all right condition. Now consider this case. So in this case, for this node, the balance factor is the height of left subtree is 1 and the height of right subtree is 0. There is no right subtree. Okay, so it is 1. And for this node, the height of left subtree is, take the longest branch, and the number of edges in the longest branch is the height. So 1, 2. So in the left side, the height of the left subtree is 2, and in the right side, you don't have any branch at all. So the balance factor is 2. Okay, so but the balance factor actually lies between either 1, 0 or minus 1. So this is an erroneous category. We should not have this kind of tree in an AVL tree. So whenever an insertion or a deletion happens to occur to these kind of things, then we have to perform a rotation for it. Okay, and the rotation that is performed for this category is called LL rotation. So the balancing actually occurs, the imbalance actually occurs to the left to left of the child. Like always think, when it is a positive value in both the category, it is your left to left LL rotation. So we have to perform a left to left LL rotation. And this is the next criteria. So in this criteria, the balance factor for this node is there is no left subtree. And in the right side, the height of your right subtree is minus 1. And for this node, listen carefully, for this node, when you are calculating the balance factor, the height of left subtree is, take the longest branch that reaches to the leaf node. So this is the longest branch. And the number of edges present in the longest branch is 2. 1, 2. So it is 2 and there is no right subtree. So the balance factor for this node is 2. And here the imbalance actually occurs to L. To the node where the imbalance occurs, to the left and to the right, we have this imbalance. So this we call it as LR. The rotation that has to be performed over here is called LR rotation. And consider this category. So here is a case where for this node, you don't have any left subtree. for the right subtree, the height is -1. And for this node, there is no left subtree. And the height of right subtree is 1, 2. So it is 0 minus 2 is -2. And this is called RR. The imbalance occurred to the right to right, and the rotation needed is called RR rotation. And consider the last category. For this node, you have a single left subtree. Okay, and the height of left subtree is 1, and there is no right subtree. And for this node, there is no left subtree, so it is 0. And the height of right subtree is, take the longest branch that reaches the leaf, and the number of edges in the leaf will be counted, 1 and 2. It is -2. Okay, we have 2, and the balance factor is -2 here. So whenever it is -2, you have to perform to the right and to the left of it. It is called as RL rotation. Okay, so these are all the imbalance category. Now I'll show you how to make it, how to rotate it to make sure we are reaching it into a balanced criteria. Okay, so now for LL rotation, you have to perform a clockwise rotation over this node. Okay, so it's always better to have some values, like when you get a confusion of how to perform this rotation and what exactly these things occurs, try to put up some values inside. For example, I'll just have it as this left to left. I take it as 10, 5, and 3 here. Okay, so 10 is the greater value, 5 is lesser than 10, so it present to the left, and 3 is lesser than 10 and 5, it present to the left. Okay, so here, without disturbing this binary search tree property, you have to rearrange the nodes. And this has to be done as a left to left rotation. So you have to make this 5 and 3 to reside as it is. So this remains as it is, and we are going to pull this 10 down. So this 10 node will be pulled down to the right side of 5. Now check the property of binary search tree. Root node value is 5, 3 is lesser than 5, and 10 is greater than 5. So it is present in right and 3 present in the left. So the property of binary search tree satisfied. And calculate the balance factor for each node. For 3 it is 0, for 10 it is 0, and for 5, 1 left height of left subtree is 1, height of right subtree is 1. So the balance factor is 0. Okay, so for LL rotation, you have to perform a single clockwise rotation. And for RR, what do? You again insert some values, 10, 20, 30. Okay, so this is all for your reference. For your better understandability, if you have a values and you know the property of binary search tree, you exactly know where to arrange the values, right? So in this category, for RR, you have to do the reverse of your LL. So perform an anti-clockwise rotation. So here 20, 30 will remain as it is. So these two nodes will remain as it is. And we are going to pull this 10 down to 20. So this will become the right node for 20. So the arrangement will look like this. Got it? So we have done with LL rotation, RR rotation. Now we'll proceed with REL rotation. So it is better to have some values always, as I mentioned. So you'll be having the root node as 10, and the value to the left of this root node should have a value lesser than 10. So I'll have it as 5. And value to the right of this node should have a value lesser than the root node and greater than this node. So I'll take it as 7. Okay. So now what happened? 10 is the root node. All the nodes present to the left side of your root node are having a lesser value. So 5 is lesser and 7 is lesser. Now when you take this subtree, so 5 is the root node and 7 is greater than 5. So it is present in the right side of it. So this is called LR. So in this kind of LR thing, you have to perform the rotation twice. We cannot do it in a single turn. So first we have to perform a rotation over this into an anti-clockwise rotation to bring it into an LL criteria. So we have to perform the rotation like, so node 10 will remain as it is. And here, these two nodes will be swapped. 7 will come over here and 5 will come over here. So we are going to make this LR in terms of LL. And you have to perform a rotation to the clockwise of it. So 7 will present in this place, 5 7 and 5 will remain as it is, and we are going to pull 10 to this place. Got it? Now the factor for this binary search tree, the binary search tree function is satisfying. Like 7 is the root node, 5 is lesser than root node, so it is present in the left side. 10 is greater than root node, it presents in the right side. The property is satisfied. And for LR, we should know, like, you have to bring that into LL and perform 1 rotations. Okay, so we need double rotation in terms of LR. That is very important. And whenever you are getting confused of it, have some values to it, and we know exactly how it actually works. Okay, so now we'll come to the last category, that is your RL category. So RL works similar to LR. Okay, so here we have to make this as RR category. So you have to perform a rotation into this place, a clockwise rotation first. Okay, if you want, we have some values for it. So we'll have 10 here, 20 here, and 15 here. Okay, so 10, all the nodes present to the right of your 10 should be greater. So 20 is greater than 10, 15 is greater than 10. It's satisfying the condition. And over here, 20 is the root node, 15 present here is lesser than 20. So it comes as the left side node of it. Now what we have to do, we have to perform a rotation here, a clockwise rotation to these nodes to bring it in category of RR thing. Okay, so 15 will be moved to the up and 20 will be moved to the, like, each time when you're performing, the property of binary search tree should not be changed. Okay, it has to follow binary search tree property. Even the intermediate steps has to follow it. Okay, so 15 is greater, it present to the right, and 20 is greater, it present to the right. So the form actually changed to RR rotation. So perform an clockwise rotation for anti-clockwise rotation for it. So when you perform an anti-clockwise rotation, how does it looks like? This 15 and 20 will remain as it is, and we are going to pull this 10 down. Okay, now the tree is balanced. You'll be having the root node, 1 left subtree, right subtree. The balance factor is 0 for all. And 15 is the root node, 10 is lesser than 15, so it is present to the right. And 20 is present to the right, it is present to the left, and 20 to the right. And since the value is greater. Okay, so these are all the basics of AVL tree. So each time when you perform an insertion or each time when you perform a deletion, we have to make sure, check the balance factor. And after checking the balance factor, if there is any mismatch, if the values are not in between -1 and 1, we have to check which imbalance it actually is, either LL or LR, RR or LL, and perform the rotations accordingly. Okay, so next video I'll show you how to insert it. I'll go for an AVL tree insertion, and I'll show you how the insertion happens there and what all, like, how the rotation actually performed in insertion. And next video I'll try to do it for deletion too. Thank you.